So let's just dive right in. Behind every smart adaptive system that you use, there's this powerful blueprint hiding in the background. And today, that's what we're going to explore. The blueprints for machine learning, the frameworks that turn all that raw data into actual intelligent action. But here's the big question, right? How do you actually build an intelligent system that doesn't just fail, one that can learn and adapt, but also stays reliable and consistent? Well, as you're about to see, this is exactly why having a structured framework isn't just a nice to have, it's absolutely essential. And we've got a pretty clear game plan to get through this. We're going to start with why we even need these frameworks. Then we'll get into the core learning styles, look at some more advanced strategies, figure out how to pick the right tool for the job, and then finally wrap it all up with how you go from theory to practice. Okay, section 1. Why do we need frameworks in the first place? Well, it's all about moving from what can be total chaos to something consistent and predictable. I want you to think of it like this. Frameworks are basically the rules of the road for your machine learning system. Without them, a project can just become this tangled mess. It's unreliable, you can't reproduce your results, and trying to scale it up is a total nightmare. These rules give it the structure it needs to actually work. Now, what's so interesting here is the huge shift this represents. The old way of doing things, the model-based approach, was all about fixed physics and equations. Yeah, it was super precise, but it wasn't very flexible. The new, data-driven world of ML is the complete opposite. It's incredibly adaptive. But it's that very flexibility that makes having a strong framework totally non-negotiable. So let's build on that and jump into the core learning styles. Really, you can think of these as the two main tools that every single data scientist has in their toolkit. First up, we've got supervised learning. And the name really says it all, right? You're supervising the machine by feeding it data that's already been labeled with the right answers. It's kind of like teaching a student with a textbook that has an answer key in the back. The whole point is for it to learn the patterns so it can predict the right outcomes for new stuff it's never seen before. And this is pretty much how it works. First, you have to label all your data. That's the answer key. Then you do something called feature selection, which is just picking out the most important bits of information for the model to pay attention to. From there, you train the model on all that labeled data, and finally, you validate it to make sure it's actually making accurate predictions. So what does this look like in the real world? Well, here's a fantastic example from our source material, trying to predict material fatigue based on a ton of stress-strain data. See, you have all the historical outcomes, the answers, and you train a model to recognize the warning signs before it happens again. Okay, but what if you don't have an answer key? Well, that's where our second big tool comes in, unsupervised learning. With this one, you just give the machine a giant pile of unlabeled data and basically tell it, go find something interesting. The goal here isn't prediction, it's all about discovery. And so the workflow here is much more exploratory. You start by cleaning up the data, and then you might use a technique like clustering to automatically group similar things together. Or you might use dimensionality reduction, which is just a fancy way of saying you simplify the data to make it easier to work with. And then, at the end, you analyze the patterns that the machine found all on its own. A perfect example of this is, say, grouping a bunch of factory machines based on their performance data. You don't tell the algorithm which ones are good or bad. You just let it look at the data and find the natural clusters. And maybe it discovers a group of super high-efficiency machines and another group that's about to break down, all without any help from you. So, if we boil it all down, the key difference is this. With supervised learning, you need labeled data because you already know the answers you're trying to predict. But with unsupervised learning, you're working with unlabeled data because you're asking the machine to help you figure out what the interesting questions are in the first place. All right, so we've got the basics down. Now, let's level up and explore some of the more advanced strategies, the kind you use when those first two tools just aren't quite enough for the job. This is where things get really, really cool. Reinforcement learning is all about learning by doing, pure trial and error. You have an agent, think of a robot or an AI in a video game, and it takes actions in an environment. When it does something good, it gets a reward. When it does something bad, it gets a penalty. And over millions of tries, it literally teaches itself the best way to do things to get the most rewards. Now, why would you rely on just one model when you could have a whole team? That's the core idea behind hybrid and ensemble learning. You basically combine a bunch of different models, and then they all kind of vote on the best answer. This team of experts approach almost always gives you a more accurate and reliable result than any single model could ever achieve on its own. And this is really the cutting edge. Neural symbolic systems are trying to get the best of both worlds. They merge the incredible pattern spotting power of neural networks with the clear, explainable logic of how humans reason. This might just be the key to building AI that not only works, but can also explain to us why it's making the decisions it's making. So, we've got all these amazing tools in our toolkit, but the million-dollar question is, which one do you use and when? Well, this next part is all about matching the right framework to the right problem. Just think of this table as your go-to cheat sheet. If you need super high predictive accuracy and you have a ton of labeled data, supervised learning is your best friend. If you want to find hidden gems in your data, go with unsupervised, but just be ready because the results can sometimes be tricky to interpret. For really dynamic tasks that change all the time, reinforcement learning is amazing, but man, is it computationally expensive. And if you need the absolute best accuracy and robustness, a hybrid approach is fantastic, but it's going to be a lot more complex to build. Okay, we're in the home stretch. For our final section, let's take all this theory we've been talking about and pull it all together into a single practical blueprint you can use for pretty much any real-world ML project. Here it is, a simple 6-step blueprint. Step 1, you have to define your objectives. What problem are you actually trying to solve? Step 2, based on that goal, you pick the right framework. Step 3, you gotta prep your data, clean it all up. Step 4, this is where the magic happens. You train, validate, and test your model. Step 5, you put it out into the real world and you monitor how it's doing. And that brings us to the final and most crucial step, which is that last step, continuously update and retrain. Honestly, this might be the most important takeaway of all. Building an ML system isn't a one-and-done kind of thing. The world changes, new data is always coming in, and your model has to adapt with it. It's a continuous, never-ending cycle of improvement. And all of this leaves us with one final thought to chew on. We are right on the edge of being able to merge that machine-level precision with human-like explainable logic. So as those two worlds start to collide, what does that make possible? What is the next frontier for intelligent systems?